Hello, everyone, and welcome to the final talk of the session. And so we have with us Dr. Soma Biswas. Soma is an associate professor in the electrical engineering department in IISc. She received her PhD from University of Maryland College Park, and after that, she worked as a research faculty at the University of Notre Dame and as a research scientist at GE Research before joining IISc. Her research interests span computer vision, pattern recognition, and machine learning. Soma, over to you. You're muted.
Sorry. Thank you so much for the introduction. I'll share my screen now. So the screen is visible, right?
Yes, we can see. Yeah.
Okay. So good afternoon, everyone. And first of all, a big thanks to the organizers for inviting me. So the title of this talk is Sketch-Based Image Retrieval. So I have divided it into two parts. The first part is introductory because the audience, many people are from different fields. So I thought I'll just keep it very simple to introduce the general idea of computer vision and cross-modal retrieval or sketch-based image retrieval. And in the second part, we'll go over the actual work and the work that's presented in the paper. So sketch-based image retrieval is one important application which falls under computer vision. So what is computer vision and why is it so important? Computer vision traditionally dealt with mainly images and videos, and it is so important because images and videos are everywhere. For example, we take images and videos of big and small events of our lives. Then there are sports videos, there are surveillance images and videos, there are medical images, and then satellite images and so on. So it's very important that we know how to store this huge amount of data, how to analyze this data, how to retrieve it as and when required. There are several challenges in computer vision. The main goal of computer vision is to essentially interpret an image or a video the same way as a human does. But it's very difficult because humans can usually look at an image or video and see the entire picture. But for a computer, they'll essentially look at just the pixel values. And with any change in the image, the pixel values can drastically change, even though the object of interest has not changed at all. For example, this slide lists some of the challenges in computer vision. The first one here, to the top left, is just the image which is rotated or the camera which is rotated. So for a human, it's very easy to say that these are images of the same object or the same person, but the pixel values, if you look at the pixel values, the corresponding pixel values, they are completely different. Then there are other challenges. For example, the object can undergo different transformations, deformations, or articulations. For example, here the horse can be sitting, standing, or galloping. There can be background clutter. There can be occlusion. For example, our goal may be to detect the number of persons or count the number of persons in a crowd, and most of the persons may not be visible totally. Then there can be other challenges. For example, say, illumination difference, scale changes, motion blur. And you also see the images of chairs, right? So if you look at this image, you will see that all the attributes or the characteristics that we can see, for example, the shape, the texture, the color, all these characteristics are completely different. So what is same? What is same is the functionality of that object, right? So the algorithm essentially has to abstract out all these characteristics and still understand what a person might do with that object. But data goes beyond just images and videos, especially nowadays with so many media types coming in. We have data stored as images, as videos, as text, as hyperspectral images, as sketches, and so on. So computer vision, essentially, though it started with images and videos, now it has gone beyond that, and it includes all these different modalities that we can potentially think of. So what is cross-modal retrieval? So cross-modal, as the name suggests, it includes two modalities. So when we talk about modality, one modality can be image or video, and the other modality can be, say, text, right? Text and image matching is a very, very popular application where we might type in something, say, for example, this kid has typed trekking backpack with the hope of getting images of trekking backpacks, right? Instead of a text, you might want to just sketch out what you would actually want, because you might want a very specific type of backpack. So you can just sketch out what is there in your mind, and then you would want to retrieve similar type of backpacks. Okay, so this is cross-modal retrieval or cross-domain retrieval, where your input belongs to one modality and you are expecting an output from another modality. So in many cases, what is done is, even though we are retrieving images, most of these images are tagged. Whether it's automatic or manual annotation, most of these images are tagged, and what is actually being compared is the tag of that image along with the input tag. That is not actually cross-modal matching. That is just text-to-text matching, right? So why do we need cross-modal matching? Because manual annotation of several hundreds and thousands and millions of data is very difficult, and it may be very noisy too. So you do not want to go through that two-step process of first annotation and then retrieval. If given the text, we can directly retrieve, it would be much better. And obviously, if annotations are available, you can always add them and generate a better output. So cross-modal retrieval has several other applications as well. Say, for example, all these, you can say these are cross-domain or cross-modal applications. For example, matching in surveillance scenarios, matching your RGB image of a face with the near-infrared facial images, which you acquire during nighttime, also falls under this, right? It has a lot of applications in forensics where a forensic artist might sketch out picture of a criminal, and then that is to be matched with the database of potential criminals. Nowadays, there are many more interesting applications as well. For example, you just take the picture of a dish, and you would want to automatically get what are the ingredients that has been used in that dish. Or, for example, what can be the calorie value of that dish, and so on. Right. So now coming to the exact problem of ZBIR, which is the short form for sketch-based image retrieval. Here, the input is essentially images as well as sketches. As you can see, you have images here and you have sketches here. So these are input to the algorithm. Okay? And then what your algorithm does is to learn a model where during testing, if you give in a sketch, then it can retrieve the images. Okay, so this is the basic idea, that during training, you have both images as well as sketches, and then you give it to the training algorithm. The training algorithm will, in general, learn a common latent space. Why do we need to learn a latent space? We need to learn the latent space so that the images and sketches of the same class, they come together, so that during retrieval or during testing, when your input is a sketch, you can easily retrieve the corresponding images. So this is different from the standard classification problem. We are not trying to classify what that input sketch is. We are just trying to retrieve the corresponding or semantically relevant images from the database. Why is it so difficult? It is difficult because the representations of images and sketches are very, very different, right? So even when we just have images, it becomes a challenging problem because there is so much of variability within each class, right? Now we are talking about two different domains. One is a sketch and the other is an image. Even within these modalities or domains, there are lots of variabilities. And now you are trying to match them. So it becomes a very, very difficult problem. Now you can always ask the question, that is, why do we need to do ZBIR, right? Suppose we have 10 classes of interest, right? So we given 10 classes for images, we given 10 classes for, say, sketches. We can individually learn a classification model. So if during testing, my input is classified as a flower, then I can just retrieve all the images of flowers. Why do I at all need to do this cross-modal matching? And that's a very relevant question. So though this research started with the training and test classes being the same, now the research has totally shifted to zero-shot sketch-based image retrieval. Because that is where the power of retrieval algorithms really plays a picture. That is, if I have not seen a sketch or if I have not seen an image, I cannot classify it because I do not have any information about that particular data. But I can still retrieve. How can I retrieve? Because this whole algorithm or cross-modal algorithm is about bringing the data from images and sketches to a common space. So I do not need to classify, right? So even if during query or during testing, the query sketch is from a completely different class. Say, for example, the query is a cat sketch, and I have not seen cat during training. It should still be able to retrieve the cat images, right? Even though it has not seen cat during training. And this is called zero-shot sketch. Okay, so it is zero-shot SBIR or zero-shot sketch-based image retrieval. So zero-shot, essentially, the name comes from the fact that I have seen 0 data points of that class during training. So if you work in this area, you would have also heard of, say, one-shot or few-shot. And it is a well-studied problem in the classification context, where we would try to classify without having seen any example, or having seen 0 examples, or having seen just 1 example, or having seen maybe like 5 or 10 examples, right? But there are some significant differences between zero-shot classification and zero-shot SBIR or zero-shot cross-modal retrieval, and I'll explain that here. But the main goal of zero-shot learning or zero-shot SBIR is that we have not seen those data during training. And why is this important? Because the number of categories is increasing day by day. And we really can't expect that we will see everything during training, right? And even if we try to build our training set like a really huge one with most of the classes that we can think of, then also maybe next day we'll get 10 more different classes. So it's really impractical to again train that huge algorithm again with those 10 additional classes. So it's very, very important that our algorithm can generalize to new data which it has not seen during training. So how exactly is it possible to classify an unseen class or generalize to unseen classes? Are there any assumptions? There is a very big assumption in any zero-shot learning, or whether it's zero-shot classification or zero-shot sketch-based image retrieval. The assumption is that the unseen classes and the seen classes, they share attributes, and the algorithm knows about those attributes. And I'll tell you what this means. Let's look at this image which shows a horse and a zebra. For example, let's assume that we know what a horse is. We have seen horses, right? We have seen images of horses, but we have never seen a zebra. But we know the concept of stripes and color. So if someone tells us that a zebra looks like a horse, but it has white and black stripes on its body, then even without seeing any image of a zebra, the first time we see a zebra, we will be able to understand that it is a zebra image, right? So this would not have been possible if we had not known anything about zebra, or if zebra did not share any attributes with the known class. In this case, it's horse. Right? So these are the two assumptions. That is, we know something about the attributes of the new class, and these attributes are shared with the scene classes. So this is used to actually classify new classes in zero-shot learning. But in zero-shot sketch-based image retrieval, it's slightly different. So as I explained, in zero-shot learning, we do need to know what that unseen class might look like. Say, for example, here we know that the unseen class zebra will have stripes, right? So it assumes that we have this information about the classes that we can potentially see during testing. In zero-shot cross-modal retrieval or sketch-based image retrieval, we do not have this assumption, right? That is because we are not trying to classify, we are just going to a common space. So you need not have to know anything about the unseen classes. You just see the seen classes, and based on only the seen data, you try to generalize to unseen classes. So this is a very, very big difference, and important one too, because we really can't assume that we will know a priori what unseen class we will see during testing. Right. So what are these characteristics and how do we get these characteristics? In our work and in majority of the zero-shot learning literature, these are also termed as attributes, and they are usually obtained from, say, word-to-vec embeddings or GLOVE embeddings. So these are pre-trained models which have been trained using huge corpus of data, text data, where the important thing to note is that you give in a word, or in this case, a class name, say, for example, zebra, horse, and so on, and you get a vector. That is, you are transforming the word to a vector such that these vectors are meaningful. For example, all the vectors of similar looking classes, say, for example, zebras and horses, will be very close as compared to, say, a zebra and, say, a fish or something else. Right, so I won't go into more details. So essentially what we do is we have the class names because it's a supervised algorithm. So we already know the class names, and we feed in the class names to the pre-trained word-to-vec model or the GLOVE embedding model, and we get the vectors, and that we treat as the embeddings or attributes. Now coming to the main part, which is the zero-shot sketch-based image retrieval. So I'll talk about some of the works. Instead of just going over one paper, I'll just talk about two works which are both quite recent, which deals with ZS-SBIR. So this is the framework for this zero-shot sketch-based image retrieval application. As you can see, I will explain what all these components are. So initially, we feed in both the sketches as well as the images. Then we have the feature extraction module, which is, in this case, a simple VGG model, right? And then we have a content style decomposition module. So what does it mean? So we assume that every data can be potentially be separated out into two parts. One is the content, and the other is the style. So what is the content and style? Suppose we take the car example, right? So we see a car sketch here, and we also see a car image here, right? So content is that part of the representation which gives the class information. So from the sketch also, we can derive that it's a car. From the image also, we can understand that it's a car. But there are several other things in the input which are not required to say that it's a car. For example, the color in the say RGB image, that is not required because the color here is yellow, but it could have been green, it could have been black, it could have been red. So that information is not required. So that color information falls under style. So whatever information, minimum amount of information required to say that it belongs to a car is the content, and everything else that is present in the image is the style, right? So as you can understand, that content is the thing that we really need to classify, right? But in this case, as I've already told you, we are not really focused on the classification part. But having said that, the embedded features definitely need to be discriminative. Otherwise, it will just start retrieving data points which belongs to some other things. So we have this content style decomposition module. And we also have a content style fusion module, which essentially says that suppose we take the content from the sketch and we fuse the style from the image, we should be able to reconstruct back the image, because the content should be shared between our images and sketches, right? So now looking at the entire pipeline, you might wonder that there's really nothing which will help it generalize. See, here we do not have any information about the unseen classes. So definitely we cannot use any information. But what is different between a standard SBIR and a zero-shot SBIR is that you ensure that the embeddings are semantically meaningful. And we ensured that by introducing the semantic vectors or the word-to-vectors in the embedding part. So we have a constraint which says that the embeddings need not only be discriminative, but they also have to be semantically meaningful. This is important because otherwise, if you just represent it as a one-hot vector, say a car is just 100 and an elephant is 001, then you essentially lose the semantic information, which is required for zero-shot learning. So during retrieval, essentially you have a query, you have a sketch. It again goes through the feature extraction part, it goes through the embedding part, and you can match it both in the content space as well as in the image space, right? There are more details, but I just try to give you an overview. Okay, these are some qualitative results where each of the sketch that you see, we have not seen it during training. Right? So this is a complete zero-shot scenario where the query is completely unseen to the training. Okay, and the red ones are the wrongly retrieved ones, and the ones which do not have any bounding boxes are the correct ones. Right? So this just shows that at that time we did better than state of the art, but as you know, this field is progressing at a terribly fast rate, and right now the state of the art is much more than this. So coming to the last part of the talk, this is a very recent work which was presented only like earlier this week in ECCV. So here it's again the ZS-SBIR problem, but here we also looked at a slightly different aspect of it. So data imbalance in training is a well-studied problem, especially in the classification context. And this is essential because really we can't assume that all the classes will have same amount of data, right? So we would not want to throw out data from the classes where more data is possible, and but we definitely need to do something about the classes which have very less amount of data. So in classification, there are lots of very, very good methods which are already published. But we then went and looked at the training data of these ZS-SBIR or SBIR data sets. And we saw that even here, the data sets are very, very skewed, right? They are highly imbalanced. But in this case, there are different kinds of imbalance which are possible. One is the domain imbalance. For example, it is possible that you have lots and lots of images, but you have very less number of sketches, right? This is the domain imbalance. You can also have sketch imbalance. That is, for some specific classes in say sketches or images, the number of data is very less. Or it might happen that for image, you have more data, for sketch, you have less data, and vice versa. So there are several combinations of imbalances that are possible in this, because you are essentially dealing with two domains. So it can be domain imbalance, it can be class imbalance, it can be a combination of both. And we actually saw that that is the actual case.
Soma, sorry to interrupt you. If you could wrap up like in another couple of minutes or so.
Yeah, sure. I think this is just the second last slide or something.
Sure, no problem. Thank you.
Yes. So what we did in this work is that we saw that there are already very, very good approaches which are available for zero-shot sketch-based image retrieval. So we really didn't want to modify the approach as such. We just explored whether it's possible to come up with a very simple add-on module which can be incorporated in the existing ZS-SBIR approaches to just handle the imbalance part. Obviously, if you come up with a better ZS-SBIR approach and then incorporate this, your results will be higher, but that was not the focus of this work. Right. So here from the data set, we computed something called the effective number of samples. It is nothing but the total number of samples per class for both sketches and images. And we use this to essentially make the embeddings better with respect to the imbalance that is present in the data set. So what do we mean by this? Suppose these big blue square and rectangle and star, these are the class prototypes or the class representatives, right? So it might happen that if you have very less amount of data in one class, then that class and the neighboring classes will start coming together in the embedding space. But with this regularizer that we proposed, so it is extremely simple. We just introduce this delta J term, which is computed from the class imbalance. We just introduce this regularizer with the cross entropy term, right? And because most of these algorithms, they do have a classification term, so it was very easy to incorporate this additional module with most of the existing ZS-SBIR approaches. We tried with the three recent ones. One is the BMVC work, which I explained before. The other two are the CVPR19 and ICV19. So these are the three approaches. We took the baseline approach and we just incorporated this AMD regularizer, and you see that with no further modifications of the base algorithm, the results do improve to a reasonable extent. Right. And these are some qualitative results. Obviously, these are some of the good ones where there is a significant difference between the baseline model and the baseline plus regularizer. But yes, we did see a reasonable difference with the other examples as well. So given a query, in some, you can see that majority of the top 5 are wrong. And with the regularizer, it was able to retrieve some of the correct ones too. Right. So going forward, I would like to stress that cross-modal retrieval is a very, very important research area, and SBIR is just one of it. And with the availability of touchscreens and all, SBIR will have several applications in future. So generalizing to completely unseen classes is not only a requirement for classification, but for these other applications as well. And we should not only look at really developing better algorithms for that application, we should also look at problems like imbalances and noisy data, or there are so many other challenges that can potentially have an adverse effect on the output. And there are several future directions too. For example, you can fuse multiple modalities. Say, for example, instead of just giving a sketch as input, you can have a sketch as well as a text as input. So even in input, you have multiple modalities. Accounting for domain differences, for example, one sketch can be like really good with which you have trained the data by professional artists. But when we actually draw on iPad or a touchscreen, we know how bad our sketches are. So it actually has to generalize to good and bad sketches as well. So with this, I'll end. Thank you.
Nice, great. Thanks, Soma, for the very interesting talk. I think it's a fitting closure to the session. We have a couple of we have a few questions. Let's take maybe a couple. One is around the technique. So is the latent space dimension optimized for the sketch embeddings and the image embeddings together? And what is the validation metric for retrieval? I think two interconnected questions.
Yes. So what we did was we didn't really try to really optimize it. What we did was the dimension we took as the dimension of the word2vec or the glove embeddings, because we said that they have to be similar to the glove embeddings. Right. So we just took the embedding as the dimension of the word2vec or the glove. But yes, I'm pretty sure that can be optimized as well, but that was not one of the focus of this.
Got it. Sure. The other one is interesting application. So can this method be extended to generation of drugs given an unseen target protein? That is graph generation based on any unseen condition.
This is really interesting, and frankly, I haven't thought about it. But these I really can't say whether it can be applied, but these zero-shot techniques, they definitely hold promise for generalization to unseen data. But whether for this particular application, I really can't say. But many of these zero-shot learning, zero-shot, and these retrieval things, I think some amount of, you can say, knowledge can be taken from this and applied to other fields as well.
Right. No, it sounds like a very interesting question.
Yes, definitely, yes.
Right. But yeah, there is some question on the question panel. If you wish, you can look at them and maybe respond on the chat.
Sure, I'll do it. I'll do it after this.
Yeah, but again, thanks a lot again, Soma, for coming over and giving this talk virtually.
Yeah, thank you so much. Thank you so much for inviting.